right, dear colleagues, dear jury members, and today we gathered to have a final public talk on the defense of the Svetlana Illarionova for the thesis entitled Deep Learning for Remote Sensing of Environment and Land Cover Analysis. So first I'm going to do some introduction of the jury and the candidate. So please, let's go to the next slide. Yeah, it's me. I'm associate professor here. I guess we can skip that. Next, please. So yeah, Mikhail is assistant professor at Center of Artificial Intelligence Technology here, and also CEO of IRA Labs, author of many AI ideas in medical vision, and the head of medical vision group here at Skoltech. So next, please. Yeah, Dr. Viktor Lempitsky has a long research career in academia as associate professor here at Skoltech and postdoc at Oxford and PhD from MSU. And one of the stars who we know for many publications in CVPR, ACCVs, and ECCV, etc. We can go next, please. So Artem Nikonarov from Samara National Research University, and he's a full professor and the head of AI Institute in Samara University. Professor Nikonarov graduated from SSAU in 2002 and received his PhD degree and Doctor of Science in 2016. And he works as the head of AI Institute and as a professor of supercomputing and computer science subdepartment of the Samara University. Okay, next, please. Yeah, so Dr. Panov received his bachelor degree and master's degree from the MIPT and also worked here as assistant professor. And now he represents Technology Innovation Institute, UAE, and research focused based on Bayesian approaches in machine learning and certainty quantification and graph analysis. Next, please. Professor Nicolai Sebe is from the University of Trento, Italy. He's a leader of Multimedia and Human Understanding Group in the University of Trento. And Professor Sebe is currently a professor with the University of Trento, where he is leading research in areas of multimedia analysis and human behavior understanding. He was the general chair of IEEE FG 2008 and several important conferences ranging from the ones that I know, like ECCV, ICCV, and the ones I don't know, like this FG. And he's the program chair of ECCV in 2024 and a fellow of IAPR. Has more than 460 peer-reviewed publications, and we are happy to host and welcome him here at the defense. So next slide, please. Professor Vana Seledets is the full professor and director of the KITE Center here at Skoltech. He received a graduate degree at MIPT as well, and candidate science and Doctor of Science degree from Marchuk Institute of Numerical Mathematics of Russian Academy of Science in 2012. And he's here since 2013. He's leading the AI Center right now, and he's an associate editor of several journals in mathematics and data science. And yeah, he's the advisor, and he will be commenting on the success of the candidate later on. Next, please. Okay. Svetlana received bachelor and master's degree from Moscow State University, and her research interests include computer vision, deep neural networks, and remote sensing. So currently she's involved in a number of projects at Skoltech, and Svetlana develops approaches for efficient and robust object recognition and their properties estimation through satellite data. She conducts study with generative models and researchers image compression approaches and their applications. Also develops algorithms for video analytics. So without further ado, I guess we can proceed to the presentation by the candidate, which should last about 40 minutes. It will be followed by the questions from the jury and then we will proceed to the questions from the audience for those people who are online. Then we will listen to the word of supervisor and proceed to the official voting from the jury members. But this is it. Svetlana, please, the stage is yours.
Good morning, everyone. I'd like to present my PhD thesis entitled Deep Learning for Remote Sensing of Environment and Land Cover Analysis. And first of all, I'd like to show some background of my study and to highlight the importance of this study. The main object of my PhD thesis is forest areas. So why do we need forest observations? First of all, we can face different ecological issues, and we need to estimate forest condition and forest properties to avoid some dangerous situations like fire spreading or flood. Also, we can solve different industrial tasks where we need to know some forest properties. So why should we use exactly remote sensing data? First of all, it allows us to make predictions and to estimate some properties in difficult to access areas. We also can conduct a rapid analysis and cover huge regions for our observations. To conduct such studies, we usually use some computer vision techniques. We use deep learning or machine learning approaches. But remote sensing, the main differs from the general computer vision domain, where we use RGB images. Here we can use different data sources. We can combine different multispectral bands. We can use hyperspectral images, and we can leverage both active and passive sensing techniques. Also, we can use these properties to achieve more robust results. So why is it important? It allows us to evaluate the damages of nature and anthropogenic disasters. We also can decrease value of ground-based observations in a large scale, like in a country scale or another huge territories. And we can provide high-level specialized data. So here is the content of my PhD thesis. It comprises 6 parts that can be considered independently or can be treated as one big study. It involves a few blocks that allows us to achieve high performance for our main task, namely forest species estimation. We will consider forest mass estimation, canopy height model prediction, and auxiliary data generation. The main objective of this study is to develop more robust algorithms through different environmental conditions and different territories, data of observations, and satellite constellations. The first chapter of my thesis is devoted to forest mask estimation and to object-based augmentation. A Google research team proposed a novel approach for copy-paste augmentation for general computer vision domain. But what is about remote sensing domain? Here we face the following challenges. They are connected with geospatial satellite data specificity, namely small data set size, different environmental conditions, rare target objects that are distributed not often evenly through the huge satellite images. We proposed the following approach named object-based augmentation. We consider the following example of building segmentation, where we have a set of building masks and we have a set of different backgrounds that represent different environmental conditions, such as forest cover, fields, or any other environmental condition that we can see in nature. So we can create new samples using some satellite data properties and specificity. We can apply different color and geometrical augmentation separately to backgrounds and to the target objects. Then we can add some shadows for target objects to make it more realistic. And then we could combine these parts to create a new training samples. Here we tested this approach using a rather small data set with building for Santa Rosa and Ventura cities. Here you can see the achieved results for our approach, and we can see that it outperforms standard approach in segmentation task. Then we applied this object-based augmentation for forest mask estimation. We can use alternative approaches or alternative tools to estimate forest mask. And forest mask estimation can be considered as a primary study for further investigation, because if we want to define forest species, first of all, we need to know where we have forested areas, and we need to know exact mass. But existing tools have their drawbacks. For instance, if we consider OSM, OpenStreetMaps, then we should remember that it's a manual markup, and it has different mismatches in data, so it is not rather precise. We also can consider different masks of low spatial resolution, but we want to produce a more precise map. So we face the following challenges. We need a model that will be robust to new regions and new environmental conditions. We face a requirement to label data set size, and we want to create an open access tools. So here is our proposed approach. First of all, we train our model using a huge data set, but with not very precise markup. So here we don't have a markup for individual trees or small group of trees. After the pre-training, using this larger data set, we use a smaller but more precise data set with masks for individual trees, for small group of trees, and we also implemented our object-based augmentation technique to create more training samples. So we compared this approach with conventional approach, and we can see that we achieve higher, more accurate results for forest mass estimation. We verified our approach for different regions in Russia, in China, in India, for different environmental condition, and it proves to be rather robust and universal for different regions. Here, another example of prediction before fine-tuning and after fine-tuning. So the results of this study are the following. We improved the model robustness to new environmental conditions. We reduced requirements to label data set, and we used geospatial specificity of the considered data. Then we will discuss neural-based hierarchical approach for forest species estimation. So it is the main chapter of my PhD thesis, and the goal of this study is to predict dominant species using satellite data. So here we face the following challenges. It is highly imbalanced data, so classes distribution isn't uniformal. Also, we face different markup faults. We need to update some measurements because particular forest areas can be cut down, and we see some mismatches in data. Also, we face a challenge connected with diversity within each class. So, for instance, here you can see example of one species, and if we consider different ages, then we can see that the patterns and texture of this forest area can vary drastically. So we need to take it into account somehow. We proposed the following approach. We consider hierarchical approach where we split our target tasks into a set of small tasks. The first one is to distinguish areas covered with forest and other areas. The next step is to train a model to distinguish deciduous and conifer areas. Then we train two separate models to distinguish species within deciduous mask and within conifer mask. Then we aggregated all of these achieved masks to achieve the final prediction with dominant forest species. We also considered some additional high data to solve the problem with data diversity within each class. So it provides additional information and helps us to solve this problem. We considered these experiments for different data sources for Worldview and Sentinel satellites. Here you can see examples of high data usage, and we can see that it helps us to improve segmentation performance. So speaking about hierarchical approach, we compared it with conventional one versus all or multi-class segmentation, and we can see that it improves segmentation results. So our method outperformed the common multi-class classification approach. It achieved more stable results for forest species classification, and we also took advantage of additional high data. The next chapter is tree species mapping using weakly supervised classification and object-wise sampling. So in the previous chapter, we assumed that we use homogeneous forest stands. But there is a specificity of inventory data. So for forest inventory data, we know percentage of each forest species within each individual forest stand, but we don't know exactly distribution of these forest species within a stand. So we usually assume that the stand is homogeneous, and we usually try to predict a dominant forest species. But in this study, the aim was to use information about dominant species percentage within each individual stand. So we aim at improving forest species markup to train more robust algorithms. Here is the proposed approach. So the commonly used sampling approach assumes that we use an entire patch, and it includes different forest stands with different dominant species, but some individual stands can be cropped, can be cut, and we can observe just a part of the stand without a dominant species. So it is a noise in the data. To prevent these errors in the data, we proposed object-wise semantic segmentation approach. Here to compute a loss function, we use just information about one individual stand. So we use information about percentage of the dominant species, and we use this information to compute loss function in the following way. We set higher penalty for more homogeneous areas, and we set lower penalty to individual stands with lower dominant species content. Then we proposed the following approach. How can we adjust markup? We used our custom loss function with dominant species percentage to create new, more accurate markup. We train our model with this loss function, and then we intersect the model prediction and the initial markup to achieve new labels. And then we train our model using this data to achieve final predictions. And here you can see results of our algorithm. So our method outperformed the common sampling strategy that usually used in such forestry tasks. We achieved more stable results for each imbalance class, and we improved the forest inventory markup. The next chapter is estimation of the canopy height using satellite data. In previous chapters, we showed that high data is important for forestry studies, but such data is not always provided with satellite images, with RGB images. Therefore, the goal of this study is to estimate the vegetation land cover height from satellite images. We can consider some alternative approaches, such as ground-based observations or measurements using drones with LiDAR. But these approaches have their own drawbacks, such as cost or a problem with cover for large territories. So here we can see the importance of high estimation in different monitoring tasks. For instance, if each year it requires a huge amount of money to observe for power lines and to detect some dangerous areas with overgrowing trees that should be cut down to prevent some problems with power lines. And exactly this task there's some requirements for computer vision models. The requirement is that the error can't be bigger than 3 meters for such tasks. So speaking about weaknesses of previous studies, we can consider the following points. The first one is low spatial resolution. If we observe power lines, then these areas are too narrow, and we cannot use satellite data with 100 or 100 meters in each pixel, so we can't use such approaches. Also, previous approaches can use classical machine learning methods, but it doesn't take into account special data, special features of the observed areas. Also, another weakness is connected with many spectral bands that are more expensive than just RGB or RGB plus near infrared bands. So the study objectives are the following. We aim at taking advantage of state-of-the-art neural networks to solve this problem. We want to reduce a necessary number of satellite bands and to create software toolchain and to verify the generated samples in some applied forestry task. As a reference data for our study, we used LiDAR measurements, and we considered two satellite data sources with very high and middle spatial resolution. The work comprises the following steps. We studied different strategies. We used some supplementary data. We conducted study with different weighted loss function, and we also considered both classification and regression problem statement. For worldview satellite data, we conducted experiments with data preprocessing and pan-sharpening techniques. Here you can see examples with our predictions obtained for regression and classification tasks. We considered both to these tasks due to the requirements of target users of this application, namely foresters. In some cases, it's more important for them to know error for exact class than an absolute error of a predicted height. Here you can see additional examples of the predictions, and we also conducted experiments with forest species classification, and this data helps us to improve the predictions. So our method allows us to reduce required number of satellite channels, and we reduce the error to 2 meters, and we take an advantage of the feature engineering in this study. The next chapter is generation of the near-infrared spectral band using just RGB bands. So in previous chapters, we have seen that auxiliary data, such an additional spectral bands, lead to high performance of model. But in some cases, additional data is not available. Therefore, the goal of this study is to create near-infrared bands using just RGB bands. We can consider the following approaches. The first assumption is that we can create the near-infrared band just using values of RGB bands and sum them, multiply them somehow, and achieve value of near-infrared. But this assumption is not correct. And here we can see the following example. We can consider green roof and green tree. So RGB values for these objects are the same, but what about near infrared? It can be used to calculate normalized vegetation indices that represents the state and the health of vegetation cover. So it is obvious that value of NDVI and value of near red differ for artificial object like a roof and a green tree. Therefore, we need another approach, and here we proposed approach based on neural networks. So if we have a huge amount of training data with examples of RGB and near infrared, then we can extract some properties using this huge amount of statistical connections, and we can see some properties that that can be described by object shape, object patterns, and we can use it to predict these values of the near-infrared band. So how can we verify our approach? We can consider some general matrices as mean absolute error or other matrices, but we can also consider some applications where infrared band are usually useful. We considered the following real cases when where RGB plus near infrared is beneficial. It is small data sets, it is data from different sources, and in these cases it's better to use not just RGB but RGB plus near. We considered the following approaches. The first one is UNet, where we just try to solve a regression problem, where we make a prediction for each pixel and then compute the difference between the predicted pixel and real near infrared band value. But in this case, we obtained blurred predictions. And another approach that we chose was based on generative adversarial network, and it allows us to achieve high performance and robust results. Here you can see examples of our predictions for different satellite sources, and also example for of forest area estimation using small data set, and we can see that using additional generated near band is beneficial in such task. So our method provided the following improvement. It improves the model robustness to data sources, and it reduced requirement to label dataset size. And finally, the next chapter is multispectral augmentation techniques that can be applied to satellite images. We consider the same problem of robust forest species classification. And here we have also multispectral data, and we apply convolutional neural network to create a prediction. But we face the following problem. If we train our model for exact region and then we try to create a prediction for other satellite image, for other territory and for other observation data, then we face a poor performance of our model. So how can we solve this problem? We can use the specificity of satellite data. Namely, the fact that for one region, we usually have more than one observation of one image that covers this region. Here we considered 6 images for the same territory during some summer period, and here you can see analysis of the data that we used. On these plots represent average values for each band for each image. And we can see that connections between these values are rather complex, so we can't just transfer from one image to another image by simple multiplication. Here you can see the approach that we use for our experiments to have more accurate experiments. We used image-based cross-validation, so we run each experiment several times for each test image to verify our algorithm for new observation data and for new region. And we can see that for the baseline approach, we have rather poor results for particular images. And for other images, the results are higher. We proposed the following solution of this problem. We have images covering the same area, and we can increase data variability using these observations. We proposed mixed channel approach where we could consider a set of images covering the same area, and we substitute some bands from one data to another data to create more training samples. We compared these approaches with other augmentation approaches, and we showed that for this task, it helps us to improve model performance. This method improved the model robustness to diverse satellite data, and it also reduced a requirement to label dataset size. During the PhD study, the following approaches and methods were developed and proposed. It is hierarchical neural-based methodology. It's feature engineering for limited satellite data, weakly supervised learning, object-based augmentation, and multispectral augmentation. Proposed methods allow one to obtain more robust results for wider spatial coverage and to use less expensive data with not so huge amount of labeled data. And here you can see the list of publications during my PhD study. Thank you for attention.
All right, Svetlana, thank you for the presentation. Now, by the protocol, we have to proceed to the Q&A session, and we should proceed by a protocol. We should proceed to external speakers first, or maybe someone in the audience wants to jump in right away and say the most important comment for Svetlana right here. If that's not the case, we'll go by the protocol then. All right. So, dear colleagues of the external committee, external members, maybe Professor Sebe can start if you have any comments for our candidate.
Yes, of course. Well, let me start by congratulating Svetlana for her very nice work. I think it's quite interesting, and given that I'm not an expert in remote sensing, I learned a lot from reading the thesis. It's also interesting to see that many of the subjects that she covered are very much related to what we are doing. Of course, in other domains, but I think it's very interesting. I do have a few comments. I'll try not to ask too much, so I will let also my colleagues, enough space for asking questions. A few things that I'm quite interesting, right? So the first is that, okay, so you're doing with remote sensing, which is quite interesting, and of course is different from just regular computer vision. But I believe one of the issues with remote sensing is the fact that you have to deal with different variabilities of images. For example, you may have occlusions from clouds. You may have the changes in weather conditions, so could be different seasons and so on. And this makes remote sensing really interesting, and also because you may have different type of data. So let me start first with the question related to how do you deal with let's say with occlusion from from clouds and so on.
Thank you for your question. So we considered the northern regions, and we faced huge problems with clouds cover. Therefore, in this study, we just used summer images, summer observations, because due to high clouds cover, we cannot use any winter or autumn observations of these northern regions, and also to deal with clouds during summer season, we can use special masks provided by Sentinel, and we also can use masks of shadow in these images, and to create predictions for new areas, for new regions. We can combine predictions for different summer high vegetation observations, and we can merge this prediction to cover all regions and to avoid areas with clouds.
Okay. But I believe if you are using near infrared, it's a little bit more robust to this type of issues. So I would imagine that this could solve up to a point the problem. And I find quite interesting your approach of doing this, estimating the near infrared band from RGB. But in some, especially in the case of, let's say, when you have occlusions like cloud and so on, this would be ill-posed. What about doing the opposite? So if you have a near infrared band, can you just infer the RGB information?
So in the study with near infrared band, we use a large amount of data. So we try to avoid the data with clouds, but to deal with such cloudless data, we prefer to use active sensing like SAR data. So this range of wavelengths like RGB or near infrared cannot provide access through clouds. So it's a real problem for remote sensing domain.
But theoretically, you can also start from SAR and try to infer the RGB data, just the same way as you did for the near infrared channel.
So we can apply some SAR data for this study, but another problem is special resolution and additional noise in SAR data. So it's another huge area for investigation for additional study.
Absolutely. Now, one thing that I like, and this is I'm just following up. I'm bringing you where I want to go. No, so one important aspect of, let's say, remote sensing is the fact that you have all these different channels of data. So you have to do a multimodal analysis. You are forced to do it. So I was wondering, have you considered having some sort of a joint latent space representation? Let's say something similar to what is done now with image and language and image, like clip and these kind of things. Have you considered doing something like that?
Could you repeat the question, please?
No. So my question is, since you are doing a multimodal analysis, I was wondering if you can just try to consider a joint space representation for all the modalities, something similar to what is done at the moment with, let's say, language and vision, so like kind of the clip space.
Yes, of course. I think it's a good idea to consider different modalities, and for instance, we can try to combine satellite images with some titles with some text that describe these images, and it might improve the quality somehow, both for representation or generation some additional data.
Okay. So let me ask you one last question, at least for now, and then I will let the floor to my colleagues. I believe an important aspect of your research is domain adaptation. And this is needed also because you may have data from different satellites, different conditions, and so on. I was wondering, have you considered something like, so also, since you're doing with satellites and with satellite images, in some cases, this data, at least the source data, may not be available. So have you considered doing something like a source-free domain adaptation, in which you have only the trained model and you are using that one to do the domain adaptation? So without having the data of the source in order when you do the training.
So in this study, yes, we try to consider different data sources. So, for instance, in the study with high estimation, these lower images in the bottom of the slide, they are for base maps such as Mapbox or Google Map. So we trained our model using world view images, and we estimated the performance using other data. And in this case, if we can rely on some texture information, that it is easier for the model to move from one data sources to another data sources. But if we use just low resolution data with a huge number of multispectral bands, then we can't rely on texture or on some patterns of forest cover, and in this case it can be more difficult to transfer from one data source to another data source.
Now, my point was a little bit, a bit different, right? So usually when you do domain adaptation, you have access to both source data and the target data, right? And then you do some kind of a joint training and you try to kind of align the distributions. But in some cases, and this is for satellite images, I can imagine it will be very likely, you may not have the source data. You may have only the trained model, nothing else. Okay.
Yes.
So then you would have to do some kind of a source-free domain adaptation. So you don't have the source data at all. You have only the model, the pre-trained model with your source data, with some data. Can you use still that one to do the domain adaptation?
So for the experiments with height estimation, yes, we could use our pre-trained model for new data sources with the same properties. I mean, with the same spatial resolution, and but I think we also should further conduct some experiments when, for instance, we train our model using RGB, and then we try to make a prediction using just a grayscale. So it is interesting to see the results for such case, because in case of high spatial resolution, I get that some textures, some patterns are more important than RGB values.
Okay. Thanks. I'll let the floor to the colleagues. Thanks.
Thank you, Professor Sebe. Victor, maybe you want to make some comments?
Sure. Yeah, congratulations. I enjoyed reading the thesis, and it was very well written, very clearly explained ideas. as Professor Sebe, I'm not a specialist in remote sensing, so I guess my questions are mostly about whether some of the ideas are here specific for remote sensing or they generalize to other domains as well. For example, so I was quite impressed with your results with mixins, and that your system does better than just regular dropout, right? And the idea seems universal. So do you think, I mean, is there something I'm missing, and is there something specific for your application, or can you apply mixin in like wherever you previously would apply dropout and get an improvement?
Thank you for your question. So I guess that it is an interesting point for the discussion. I guess that we can find some cases in other computer vision domain where we can apply such approach with multispectral data. Probably it can be useful to detect some plants diseases that can't be seen just in RGB spectral, but it can be seen for different multispectral bands, and we can try to apply this approach in such cases. So I think so.
Okay, but like imagine you take some standard neural network architecture, convolutional architecture, VGG network, and you put in a color image. And then somewhere in the middle of the network, you would have 256 channels. So it's sort of multispectral. Then can you apply mixin at this point? Can you replace some of the channels in this tensor with the channels of other images in your batch? Would that help, do you think?
I think it would be an interesting study. We have not conducted such experiment, but I guess we should try to do such experiments with augmentation of channels.
Mm-hmm. Okay, then I was also curious that hierarchical classification in your case worked so clearly better. Again, the question is it some specifics of your task, like the balancing between classes, or do you think, because previously I think like 10 years ago, there were some papers that would consider fine-grained classification and tried to use some class structure, but in those works somehow, I think, never won over the community. So again, do you think it really depends on the... So what is specific about your task that you think makes hierarchical work better in your case?
So I guess it's a specificity of the considered task because it based on some physical or biological specificity of this data, because we can split forest types into deciduous and conifers. We can also split land cover observations into areas with forest and without forest. then we can fine-tune individual model within this subset of data, and it is easier to perform some balancing techniques between these entire classes. So for this task, I guess it's a matter of data specificity, and I'm sure that for some other domains, we can find some similar examples where it can be beneficial.
By the way, have you tried sharing some initial parts of the classification networks, the binary classification networks? So I presume, so have you tried that? I mean, so if I got it right from the text and presentation, your binary classifiers are independent, trained independently. So I wonder if you share the weights in the initial layers. Have you tried that? Do you think it could help?
So it's another interesting option how this study can be extended, such to train a neural network with a set of outputs and try to classify at the same time different stage of the hierarchy, but in this study we have not considered such approach.
Yeah, that's fine. Okay. Yeah, but so that's all for my questions. Yeah, thank you. That's a very solid thesis.
Thank you for the comments, and Maxim, maybe questions also. We can't hear you though. Yeah, there is some connection issue.
Yes, because the microphone looks as if it is connected.
I can hear Maxim, but the sound is very choppy.
Yeah, it's the same for us.
Okay, Maxim, maybe we will, as a suggestion, maybe we will switch to one question, one comment from the audience, and then go back to the online questions while you're fixing that. Professor Nikonov, maybe you have some comments?
One moment. Yes, thank you. First of all, thank you, Svetlana, for your very interesting work and brilliant presentation. And actually, your work is very close to our works with remote sensing data and multispectral and hyperspectral data. So yes, your work is actually interesting, and of course, it's very nice. And I have some questions, maybe related to remote sensing domain, and maybe it's not an issues, but the points for discussion. So some of them was previously asked, for example, about the clouds, about the multimodal data mixing. But first, my question is about your trees augmentation technique. How do you deal with the shadows of the trees? Do you model the shadows, or do you take in account the sun position during your augmentation process, or vice versa?
Thank you for your question. In this study with this accelerate tree data creation, we did not consider sun population, and we created each each sample with the same the directions of the shadows for each augmented tree, and it was sufficient for this task.
Okay, thank you. And the next is when you speak about the satellite data, can you provide us more details about the atmospheric correction model do you use, which you use? It's important for section 4 and especially for section 8. When you use your mixing algorithms, it's actually interesting what the atmospheric correction model do you use? Something like ModTran or more complex model?
So for this study, we used the following tool. It is CentOCore. This tool is provided with Sentinel satellite data, and it is a commonly used approach. So it's like a conventional tool for such data preprocessing. It provides data in L to A level, which means with atmospheric correction, and it reduces some effects of atmosphere, and this correction is based on a set of lookup tables that are created by lib-retrun model, and it's a rather old approach for such satellite multispectral data correction.
Yes, thank you. But maybe you conduct some ablation study about the relation of some atmospheric correction to the quality of your data augmentation or segmentation techniques.
So in our study, we just used the conventional approaches, and we of course performed some literature review to find out the most commonly used approach with normalization, atmospheric correction, and speaking about nature or about origin of different atmospheric effects that can affect our model prediction. In our case, for northern region, we cannot gather a sufficient amount of training data. We just have a few observations, so we cannot add into our model, into our input data, some features connected with sun population or with exact data, because we have just a few such observations.
Yes, thank you. And I think the last question is when in section 4, at the last point of section 4, you speak about some different CNN models, but what exactly your recommendation of CNN model for worldview and for Sentinel data?
I guess we should have the following takeaway messages from these experiments. We can to create a robust model. We should take into account 3 points. The first one is architecture of our models, because our experiment showed that the quality can differ for different data sets, for different features. And the second point is that we should create a more optimal pipeline for classification. And the third point is that we should consider exact specificity of our data. So we should include some pre-processing. We should understand the origin of the data and to work with this data.
Okay, thank you. And the last, yes, thank you for adding the PSNR quality measure for your near-infrared synthesis. Yes, it's interesting. 26 or 27 decibels. Yes. So thank you for your presentations, and thank you for your answers.
Thank you.
Yeah, thank you, Professor Nikonarov and Professor Belyaev. Mikhail, you.
Maybe we'll try Maxim.
Oh, Maxim is back. Maxim, you ready? No, unfortunately,
we can't
no.
hear you.
Unfortunately, same issue. We can't hear you.
If you want, you can text me your your comments to Telegram, and I'll read them out loud.
Yeah, maybe Maxim can try to reconnect.
Yes, the sound is coming, but it's still choky.
Yeah, thank you for the presentation, and this is an excellent work. I really like it. As a CEO of a computer vision-based company, I know all these challenges pretty well, and obviously you all the times you want to have a lot of data with careful annotation and rich annotation. I mean, I don't know, segmentation labels rather than classification labels. But again, usually this is not the case. You don't have enough data. And even if you think that this is enough and you try to apply your model to, say, a different domain, in your case, it's, for example, different, I don't know, region or a different type of camera or whatever, yeah, it will likely fail. And so, yeah, I appreciate all your efforts to make your models generalizable. It's really important. I have some questions. I feel that at least some of them kind of a follow-up of the previous ones, but I still think that it's worth asking. So first, so there are kind of two main groups. The first one is that I want to discuss a couple of technical details. Just don't want to spend a lot of time, but still, I just wonder, this hierarchical approach, how many models do you use there? Is it? You mentioned that you have several models. Maybe could you please open the slide? I just tried to understand and didn't get the point. Yeah.
So for this study, we trained the model to distinguish conifer and deciduous, and we trained the model to distinguish classes within conifer and within the deciduous areas.
So 4 models in total?
And we can also include a model from the previous chapter with detailed forest mask, and then yes, we have 4 models for this task.
I just wonder, have you tried to just kind of do hierarchical segmentation just within one model? You can just simply modify your outputs in a loss function to take into the account that you have kind of some hierarchy of classes. And if it didn't work, I just want to discuss why.
No, we have not conducted such experiment, and as I have already mentioned, it would be interesting to conduct experiment where we combine all this hierarchy within one model. So it is like an extension of this preliminary study.
Yeah, okay, yeah, thank you. And I just wonder, so here you basically, your results show us that if you add this height classification model, it really helps. And for some of the following chapters, it's clear that you train, that you kind of get some benefits when you train, say, a generative model on a larger data set. And then in some sense, you kind of, it's a way to avoid these very small data sets, annotated data sets. But here it seems that you train your height classification model based on the same data set, or it's not correct. And here again, you use some kind of large external data set to train this classification, height classification model.
Yes, for this study, we have different areas for these LiDAR measurements that we can use for our study and to train our model, and areas with inventory data that we can use for some classification approaches. And in some cases, we can also use inventory data with height of each individual stand.
I'm sorry, let me be more specific. So within these computational experiments, did you use a different data set for height classification, or it was just the same data set that it was used to train the whole pipeline?
This data set is the same data, but here we did not apply high estimation model. We assume that we have already generated this data.
But still, I mean, you still have this height classification model, right? So it's a model, or
here it's like layer, input layer. From
it's just
yes.
Okay, it's just kind of an additional channel. Am I correct? Yeah, I see. Yeah, and well, thank you for clarification. Yeah, it makes sense now. And kind of the second part of kind of this group of questions is related to using different parts of your research together. So, for example, have you tried to apply your object-based augmentation for this particular part of your research? And so I understand that kind of a lot of additional experiments, obviously combinatorial one, right? But still, I just wonder if you, at the end of the day, you want to create the most accurate model for species classification, it seems that you need to combine all these ideas into one very solid pipeline.
Yes, currently we are working on such experiments, and currently we use all these approaches, all these results for current projects at Skoltech to create a more robust maps with different environmental properties.
Yeah, so in some sense, it's kind of a more industrial project, right? Here you research different components, and then you just want to create a really solid product or service. Yeah, okay, thank you.
Thank you very much, Mikhail. Maxim, shall we try again? Probably not. All right,
I would suggest that Maxim can just type his questions in chat.
You already did.
I already
Okay.
sent it. I don't see the chat on the screen here.
Okay, so Svetlana, 2 questions from Dr. Maxim Panov. Number 1, in many CV and NLP tasks, machine learning models achieved at least human-level quality of prediction. Of course, there are still many issues with robustness, but generally the quality is impressive. What is your assessment on the state of the art for remote sensing? Are we already there, or still there is a room for significant improvement? If you, by the way, if you open the chat on your own laptop, so you can also see this question.
Thank you for the question. Of course, we conducted a literature review. We observed other approaches, other state-of-the-art approaches in forestry tasks, and the aim of this study is exactly to bridge the gap in the following question. It's a model robustness. In a lot of studies, we can just consider a small amount of data, so a small region, and create a prediction for the closer area for the same satellite data. Of course, such approaches are beneficial for in some cases, in some applications, but if we want to produce a large scale and a high quality prediction with high spatial resolution, then we need to improve such approaches and to verify our algorithms for different regions. It is difficult to compare our approaches with other approaches or algorithms that because in this specific domain we face different limitations with data availability, and we can just conduct a similar studies with the same machine learning or deep learning algorithm, but we cannot access the same test areas. And in our studies, for some region, we also share this test and training data set. So I guess it's also an important contribution of this study. And speaking about exact numbers, as I've already mentioned, it's difficult to provide an exact answer, but comparing with other approaches using the same algorithms, they showed advantage of the proposed approaches.
So I guess there is a second question by Maxim. So augmentation seems to be important to improve the quality of your problems. Is there a possibility to increase the data amount directly via obtaining more labeled data? Is there unlabeled data to extend the data via labeling? And so that's pretty much the question.
So the second part of the question seems close to some active learning technique when we create new labels from unlabeled data and training our model using some initial data set. Of course, it's a very interesting approach. And in our cases, of course, we need a manual markup to assess the quality of our algorithms. And in many cases, we can use as a baseline for manual markup for some tree cover area. We can use prediction of our model and then improve these labels. And speaking about creating a huge data set, it time consuming procedure, and if we want to create predictions for different environmental conditions for different regions, countries, of course, it's difficult to gather manual markup. And as I shown some examples such as OpenStreetMaps, this markup requires some updates.
Thank you. I see that Maxim already acknowledged he's happy with the answer, and yeah, it was very reminiscent of active learning setting, the one that you were describing. So thank you. And I will also, before we proceed to the questions from the audience, I think I have to ask a formal question to all the jury members. So you saw the revised version of the thesis, and it's just a general question to everyone. If someone has to comment that something is not addressed, please speak up. Otherwise, we'll consider that all the changes are satisfactory. So I see that in the audience, everyone is happy, and maybe our team of external members are all signaling that the changes are satisfactory. Thank you. Especially wearing the same color attire. So thank you. No coincidence. Okay, so let's proceed to the questions from the audience. I can see that there are questions that overlap in the chat. I see one particular question regarding the data. How did you choose the sources of data in particular countries, and is this data public?
So thank you for the question. We used inventory data for northern regions, and a part of this data is available. Another data are not available, and also you can use the results of our study in some open access services like GeoAlert services, or it will be available in some Skoltech projects for environmental studies, as we are working now on different tools and different tools for environmental studies.
Okay, and I can see that the question about clouds was already asked by Professor Sebe, and Dr. Panov asked the question about state-of-the-art in collaborations. So the only question remaining, the technical one, the acknowledgements to researchers that has been done, that's well addressed in the thesis. So do we have any other questions in the chat or maybe in the audience here? Okay, just since I'm also a jury member, I'll ask my question then. So if you take a look at the RGB camera, it's never just RGB. There is some spectral sensitivity, right? So even green sees some red, right? And so the classical approach to estimate near infrared is to take red channel and assess the tail of the sensitivity, because silicon, the wafer that it's made from, is actually senses some of that information in the near infrared. And that's like typical pre-neural network approach. So I was wondering if you could use that for your cycle gun as a regularizer, as you would actually limit the values of intensity to something realistic that sensor can measure. Am I clear, or is this?
Thank you for the comment. So it's interesting question. We have not conducted experiments with such measurements, but so probably it should be also investigate.
Thank you. So with that, we complete our Q&A session.
And now one more question from the same user, yes, from Violeta, remains, as she says, not read and answered. I think the reference is for question number 5. So the citation is as follows. What about comparison with other researchers in Russia, world, for the same tasks by the time of your experiments and by now? If you can see it in chat as well.
Thank you for this question. So if we compare changes in the studies during this period of time, I guess that the same problems can be faced with data limitations and with objectives to create less expensive data. So I guess that we can combine some new state-of-the-art neural network approaches such as diffusion models or transformers that have not been presented in this PhD study, and we can combine these novel approaches with some ideas from the presented study, and I hope it allows one to improve model performance for different environmental tasks.
Thank you. Any other questions?
No, I can't see any other questions in chat.
Okay, thank you very much. So with that, we proceed to the next deliberation session. It's a closed session, so we kindly ask a candidate and the supervisor to let us discuss the defense and do the voting.
First of all, I'm sorry, but according to our regular procedure, we first give the floor to the supervisor of the thesis, and then we move.
I apologize for that.
That's
Professor
fine, yes.
Asiladis.
And then we proceed to the closed deliberation and voting.
Okay. So all the questions. Okay. So all the questions about the content of the thesis, so I think were asked, and there is no doubt to me that this is a very high quality work. I will just want to say a few words about the personal qualities of the candidates. So Sveta is extremely hardworking, and you may guess it from the number of publications. So she's like every day at work, and like if the paper is not published in 3 months, she's unhappy. So that's sort of a good quality for a researcher. And she's really passionate about the topic of remote sensing. And I'm not also an expert in remote sensing at all, but she was like, I want to do this. And she was doing different methods. Well, I really hope that after she defends, she will be able also to look outside the box a little bit and see that the methods that she's developing are applicable not only to remote sensing things as well, because they're actually quite interesting, and maybe some new collaborations will start after that. But again, I'm extremely happy with her work, extremely happy with her performance, and I'm pretty sure that she will be very successful. Yeah, I think that's all. And she's a very nice person also. Okay, thanks.
Thank you, Professor Saledis. I'm happy we heard that, and now we can proceed to that session.
Yes, so Svetlana, Ivan Valerievich, and colleagues, please leave the room.
All right, so let's proceed to the final announcement. Svetlana, congratulations. All jury members voted for accepting the thesis as is and the presentation as is, so no changes are necessary, and congratulations to the PhD. No, we're not voting, not clapping.
So thank you, everyone. I'm grateful to my co-authors, to my scientific advisors, for Professor Siledits, for support during my PhD study. I'm also grateful for my co-advisors and committee members, Dr. Vladimir Ignatiev, Dr. Dmitry Shadrin, and for my co-authors, for other students who helped me during my PhD study, for the discussions and fruitful discussions of the scientific topics, and for their support. Thank you, everyone.